Our modern universe is a complex mosaic of matter.
When we marvel through our telescopes at the fantastic structure of our universe and its galaxies, you gotta ask, where did that come from?
Matter in the universe arranges itself on a vast cosmic web. Galaxies and galaxies clusters are strung out on sheets and filaments.
It seems this intricate web is organized by a cosmic architect. Space-time. It shaped everything, from planets to galaxies, atoms to cities.
The universe is made of space-time. Whatever the substance is, time and space bound together, that's expanding and creating the universe we see around us. It's everything. Space-time is what the universe really is.
It's a hard concept to grasp, and even harder to visualize. Scientists observe the universe in different wavelengths of light. This is the sun, in visible light, X-ray, and ultraviolet. Now imagine if we could see it in the space-time spectrum. We would see space-time distorting as objects move through it.
Space-time can warp and push things around. It can expand and pull things apart.
Allows you the same thing.
But it's the shape of space-time that dictates how we experience it.
Imagine you're in your car. You go up hills and you go down hills. So the shape of Earth's surface determines how you travel across Earth's surface. In the same way, the geometry of space-time determines how light and matter move through space-time.
The rules are simple. Matter, in fact, any object, tells space-time how to curve. The curvature of space-time tells matter how to move.
Because the shape of space-time tells matter how to move, what we call gravity, this means that gravity and the shape of space-time tells matter how to clump together and form larger and larger structures.
But at the beginning, the space-time landscape was very different from today's. And the very first matter started to change the shape of space-time.
So this space right here has a tiny bit more matter in it than this over here. Wherever there was a little bit of extra mass, that would bend space a little bit more. Well, if you're bending space a little bit more, then more mass would collect there.
In the early universe, the denser regions of matter created deeper curves in space-time.
And as the mass gets bigger, as stuff falls into that well, it gets deeper and deeper and deeper and attracts more stuff. And it's just a runaway process.
Gravity increased, pulling in more and more matter.
Got more dense, got more dense, got more dense, and then before you know it, you've got a star, and you've got a bunch of stars, and you start to make a galaxy. And these stars evolved and began forming large structures. They sort of burned through all their nuclear fuel and exploded, and they made all the heavier elements. And with time, we got down to having things like planets, atmospheres, people, all the things that we care about today.
All of this started out as energy fluctuations in expanding space-time.
These, at first, very tiny fluctuations became these gigantic structures that we actually see today.
And over billions of years, that material began to coalesce into individual galaxies, stars, planets, and you.
Fluctuations in the expansion of space-time laid out the pattern of the universe. The curvature of space-time controlled the evolution of everything we see today.
If space-time didn't have that property in bringing mass together, then all we would be is a thin haze of hydrogen gas. Not a very interesting universe at all.
If space-time didn't curve because of matter inside of it, the universe would be a really weird place. I mean, there'd be no gravity. There'd be nothing to make things stick together.
No force of gravity means no stars, no planets, and no people.
We owe our existence to space-time. But even scientists struggle to understand it.
I wish I knew what space-time is. We know things about space-time, but at the same time, we feel like we know almost nothing about space-time.
Then, in 2015, we caught a break. And for the first time, we heard ripples in space-time, generated by one of the most violent events in the history of the universe. The universe is filled with space-time. We think it's been around from the beginning of everything, quietly pulling the strings of the cosmos. And sometimes we get a glimpse of this elusive puppet master in action. 2016, astronomers witness a strange optical phenomenon. A weird circle of light, like a cosmic halo.
This is actually what you would see in the sky if your eyes were as sensitive as a telescope. They're real. This is not some artifact of how we adjust the images. Something is actually bending space and time itself into a lens.
That something is a red galaxy, which is over 7 billion light years away from Earth. It's bending the light from a blue galaxy, which should be hidden behind it. It's called gravitational lensing.
Gravitational lensing is an amazing phenomenon because it demonstrates explicitly what Einstein told us, that space is curved. And space acts like a lens, just like the lens in my glasses act. And when we look out at the universe, we see all of that. It's remarkable.
Mass from the foreground galaxy creates curves in space-time, which we know as gravity. Light follows those curves and is warped, so it bends around the galaxy.
Massive objects, like clusters of galaxies, can bend the path of light through space-time, a lot like a piece of glass can bend the path of light. So when we look at a distant galaxy, as the light passes through a galaxy cluster, we see multiple images of the same galaxy. We see arcs and circles, as if that galaxy cluster were made of glass. We are seeing the warping of space-time literally played out in front of our very eyes.
Gravitational lensing gives us a way of seeing the effects of space-time on light. But it's only an indirect observation of space-time. Could there be another way of experiencing space-time right here on Earth?
Not everything that happens in space can be seen. Sometimes you have to listen for it as well.
Believe it or not, space is a material much like this iron sheet. And like this iron, space can distort. If I put a very heavy weight on this sheet of metal, its shape is going to change and it's going to distort. Amazingly, space can carry waves, and so can this iron sheet. But to get this sheet waving, you need something really powerful. Something like me and my hammer. Did you see those waves travel through that iron sheet? Well, waves pass through space in exactly the same way. We call these gravitational waves.
Gravitational waves are vibrations from cosmic events transmitted through the material of space-time.
To set off waves in space, you need the biggest, baddest, most powerful events in the universe. Something like the collision of two black holes.
When two black holes collide, the energy released sends shock waves through space-time across the universe. By the time they reach Earth, they're so small, they're immeasurable. Almost. In 2015, scientists at the LIGO Observatory made a groundbreaking observation. They detected ripples in space-time, gravitational waves.
Rumors began flying, but it became clear after a while that this was indeed the first direct detection of gravitational waves seen by man-made instruments on the Earth.
When we discovered gravitational waves, it had been so long that we've been waiting for signals. Not only did most of us not believe it, I went so far as to be so skeptical as to look into all kinds of conspiracy theories for ways it could be fake.
When I saw this data, I still think back on it now, and the emotional impact it has on me. The only thing comparable is when I saw my daughter's face for the first time after she had been born. It was that kind of an emotional impact, just having all of this thing that we had worked for coming to fruition in one moment. It's mind-blowing.
We can actually hear these gravitational waves on Earth.
Part of what makes this so amazing, it's a bit of a coincidence, but it's a really cool coincidence, is that the signals that LIGO actually measures are in the same frequency band as the sounds that the human ear is sensitive to.
We can hear the waves change frequency as the two black holes get closer and collide.
It's a swoop up in frequency that sounds like...
What we were hearing in that were two black holes that are orbiting around one another and then coming together. That was it.
Listening to ripples in space-time has given us a powerful new tool to investigate the universe.
We are now hearing things in gravity for the first time. It's a sense that we have never been able to apply to the universe, and we're beginning to learn what is out there.
The observation of gravitational waves from black holes is one of the most significant findings in astronomy by anyone in the recent 100 years.
It's hard to overstate the importance of gravitational wave astronomy. Much like when Galileo first pointed his telescope at the stars to see something new, we now have an entirely new window into the universe.
Gravitational lensing and gravitational waves offer us an insight into the complex relationship between gravity and space. But what about the other half of the equation? Time.
But it turns out, it's space-time. Gravity not only distorts space, it actually distorts time, too.
We think of time as something that can't be changed. It simply flows ahead at a constant rate. But that's not the universe we find ourselves in.
In some crazy circumstances, my time might even, according to you, stop.
It might even be possible to travel through time and go back to the future. For sci-fi fans, space is the final frontier. For scientists, exploring time is a much bigger challenge.
Originally, we thought of time as the same thing as the sun rising and setting, but now we've come to realize that time is a more fundamental concept than that.
Time isn't just something that passes. Time is an essential part of our universe. It's part of the fabric of space-time. The Big Bang was the beginning of space and time. Since then, space has been expanding, and time has been ticking forward. It's been doing this for 13.8 billion years, creating the universe we see today.
Space and time are tied together. They're the same thing.
So, when matter influences space-time, it's not just creating deformations in space, it's also affecting
Blue, what it do?
This is where space-time becomes really cool.
Just as gravity bends space, it also distorts the flow of time.
This isn't how we perceive time. This is actually the rate at which time flows.
Very massive objects can warp and twist space-time itself. So not only is space distorted, but time itself can slow down or even stop.
The stronger the gravity, the greater the distortion.
What has the most gravity? A black hole.
Out in space, near a strong gravitational tug from a black hole, clocks can do funny things, and this is where things start getting really interesting.
around the black hole, space-time warps and twists, slowing time down. Scientists dream of sending a probe there to test their hypothesis.
Pretty good, bro. How you doing?
There's a famous way of thinking about this called the twin paradox, where two twins are born at exactly the same time, right? So they're the same age, but one of them zips very, very close to a black hole, hangs out a while, and then comes back.
If I had an identical twin who stayed back on Earth while I flew near a black hole, when we had our daily video phone calls, he would see me go, spoiler, and I would see him say, oh my goodness, I'm a little bit concerned about you because you're talking so funny. We would literally notice that time is running at a different pace for the other one.
The closer to the black hole, the slower time passes.
If instead of coming back home, I accidentally fell backwards into the black hole, my twin back on Earth would see me slow down even more. I'd go, oh, and completely grind to halt and seem frozen on the event horizon.
Time appears to stand still.
I would just have this sinking feeling that I would never be able to come home again.
But if the twin could escape from the black hole, he would be returning to the future.
Maybe it's only been a few days or weeks experienced by the one that traveled to the black hole, while the other is, gray-haired and has grandkids by now, has lived decades here on Earth.
The black hole warps space-time so much that the ultimate science fiction fantasy becomes reality.
Time travel is a staple of science fiction, and we know that time travel into the past appears to be ruled out in our universe. But time travel into the future is totally acceptable.
Time travel isn't possible just yet, but space-time has a very real effect on our daily lives. It controls how we age.
The key to different rates of flows of time is gravity. If you experience a different gravitational environment, you will have a different flow of time. As I climb up these stairs and I put myself further away from the mass of the Earth, my own clock runs a little bit faster. If you go down closer to the surface, the more your clock slows down. We have sensitive enough clocks that we can measure this different flow of time.
Exaggerate this effect, and we would see the flow of time change in front of us. Those closer to the Earth would look slowed down. Those higher up, the opposite. Which means the wealthy in their penthouses actually would age faster than people on the ground.
This is a mind-blowing concept, but it's reality.
Earth's gravity even controls time high above the planet. 12,500 miles up, there's an array of global positioning satellites, crucial to the navigation systems in our cars and cell phones.
We here on Earth use the global positioning system as a way of getting around. Okay, most people these days would be lost if they have to go more than about a kilometer from their house unless they have their GPS app on their phone to tell them where to go.
The GPS receiver in your cell phone bounces signals over 4 satellites to figure out exactly where you are. It's an exercise in precision timing. On board each satellite is an atomic clock. The weaker gravity in orbit means the satellite clocks tick fractionally faster than those on the ground.
If we didn't know to correct for the fact that the clocks in our satellites move at different rates, the GPS system here on Earth would not work.
It would actually lose accuracy at such a rate that the entire global positioning system will become useless in less than an hour. We correct for that every moment of every day.
Space-time has controlled every phase of the universe's evolution since its birth. Now, we're discovering space-time will also dictate how the universe will die. started with a bang, 13.8 billion years ago. It's been expanding ever since. Will this expansion last forever? Or will our universe come to a violent end?
For almost 100 years, we've now known that the universe is expanding.
Everything in the universe is expanding away from everything else.
We can test this by measuring light from exploding stars. Type 1a supernovas all explode with the same brightness, so scientists can accurately work out their distance from Earth. For decades, astronomers have measured this light being stretched by expanding space-time.
The universe is expanding, and there's matter in it. That matter has gravity, and that is distorting the curvature of space-time.
So it made sense to us that as the universe expanded, all of the matter in the universe would hold on to each other gravitationally.
If there's enough matter in the universe, it can actually pull on itself enough that the expansion gets slower.
But in 1998, astronomers took new measurements and made a sensational discovery.
People had expected it to be slowing down, to decelerate, but instead they found the opposite. The expansion is accelerating.
If expansion was slowing, then these distant lights should seem brighter. Instead, they were dimmer. They were getting farther away, much faster than expected. It could only mean one thing.
That expansion is getting faster.
Oh my
It's
God, it
accelerating
keeps
every
shifting.
day.
But that's basically what it's going to look
This
like.
discovery
Something
turned
like
our
this.
understanding of the universe upside down.
For the first 7 billion years of the universe, the rate at which the universe was expanding was going slower and slower. But then something crazy happened. It was as if gravity had become the opposite. Instead of attracting the galaxies, it was almost as if it was pushing them apart.
That's a very surprising result. We're still struggling to understand.
Was gravity losing its power? Or was there something else pushing space apart?
There's another ingredient in our universe, an ingredient that behaves
You know
very
what? I might actually go get some breakfast. I'll be back up in here in a little
Dark
while.
energy.
Like space-time, dark energy is...
I'm getting hungry.